The next talk is by Igor on model checking linear time properties of parametrized asynchronous shared memory pushdown systems.
Can I try to use this? Does it work? Yes. Thank you very much. So this is a joint work with Marie Fortin and Anka Muszol. Marie is here somewhere in the room. And this is a long title, but this way you don't have to read an abstract. So this is about parametrized, asynchronous, and recursive systems. Here is a crude drawing. So what we are looking at is parallel composition of identical processes for a moment. And each of these processes is recursive, which is symbolized as being a pushdown automaton. And communication, it will be the simplest case, is by shared variables. And the main point here is that we don't have locking or more complicated operations like test and set, for example, which would be like conditional writing to a register. So when these components are finite state, this setting is parametrized setting is very well studied since seminal paper of German and Sisla, and there is even a very nice book summarizing all the facts known to 2015. But here we have each component as a pushdown automaton. So here's this pushdown, and one of the important things you need to bear in mind is the undecidability barrier, which comes from this setting where you have two pushdowns communicating by the register. Okay? So once we can turn one pushdown around, and these two pushdowns behave as a Turing machine, with two pushdowns being a tape. So you can move left and right by pushing to one tape and popping from the other, and vice versa. And this is gives some limits to what we can do and what we can verify. And somehow, surprisingly, parametrization here helps. So this was noticed by Kalun. Instead of two machines, when we take a number of machines, which is not determined, communicating via, say, one register, then what happens is this model becomes decidable, at least for reachability. And how you would do this, you would first look at one machine and see what it can write to a register given the initial value in this register, and we'll compute the set V1 of all possible things that can be written. And then we'll compute the set V2 of what one machine can do, assuming that these values from V1 can magically appear on the register. Magically means that there will be some other component that can, on demand, write this value to the register. So you see, you will do this saturation procedure and you compute bigger and bigger sets, V1, V2, etc. And since the number of values here is finite, okay, this is finite valued registers, you get the result at the end, and this will be the correct result. So we are in between two cases, the unparametrized setting, which is undecidable for kind of the obvious reason, and the parametrized setting, which is kind of easily decidable. At this moment, I may tell you about two other approaches to get decidability of approximating this setting of two pushdown systems communicating via the register. So one is bounded context switching, where we kind of allow bounded number of communications between these two pushdowns. Another one, we kind of cut communication, but use some weak form of lockings, which is nested lockings. And this is the third one, which we'll talk about in this talk, which is this parametrized setting, which turned out to be easily decidable. So this talk will be about something in between this easily decidable setting and this undecidable setting here, which is a model where we add a leader process to this parametrized setting. You see, so it's somehow like this setting with two pushdowns, where the second pushdown is replaced by some number of copies. So this is one leader that runs its program, and there is an undetermined number of contributors that run another program. This model was proposed by Hag in 2011, and then it was studied in several papers, in particular these two papers that appeared in this conference, so by Esparza, Ganti, and Majumdar in 2013, who gave exact complexity for the reachability problem, and another paper in 2015 where they studied repeated reachability problem. And I should underline here that it's important that we have only register reads and writes, and we don't have this test and set, and we don't have logs, because otherwise we would go back to this setting of 2 pushdowns, because we kind of kill all the parameterization with logs or with test and set. So how this model looks like more concretely, suppose we have this leader process D, which writes some 1 to a register and then reads 2 and 3, and then writes a hash value. And there is the contributor, which reads 1 and then can write either 2 or 3. And then you see in this model, in order to see hash value in a register, in order for the leader to write the hash value in the register, we need 2 copies of C. First reader would write 1 to a register, and then 2 copies of C would read this one. And 1 copy would then write 2, and the second copy would write 3, this will be read by the leader, and this will write the hash. Okay, so this shows that sometimes you need more copies than 1, and this also shows how this thing work. And the reachability problem asks whether we can see hash value in the register. It's a general, simple formulation of this problem. So if there is a number of contributors, and there is a run such that we will see hash in the register. More formally, the model is we have a contributors that is a transition system. We have leader that is a transition system, maybe infinite transition system, and they run in the interleaving fashion. So here is a leader, this green line. Here is the value of the register that goes along. And then there is some number of contributors and contributors. So first a leader does a move A, and then one contributor does a move B, and then another contributor does a move C. And this moves depend on the value of the register, and that can change the value of the register. So, and this is interleaving semantics. And then you can see that this is infinite in both directions, in a sense that the number of contributors is not bounded, and then the states, these S's, are also infinite because they can, these are configurations of the stack machine. Okay? And then, well, just from the semantics, you can see that instead of this tuple of states, you could take a multi-set, and in some cases, you can take a set. So, for example, if you are interested in reachability, it's correct to consider just a set of states. But for repeated reachability, it would not be sound to take a set of states. You need to stay with multi-sets. So what are the results? What do we know about it? At least some of the things we know. So Hack, when introducing this model, has shown that it is decidable. Then Esparza and co-authors shown that it's p-space complete, the reachability problem. And we have shown that it's actually almost always decidable, in a sense that they were looking only at pushdown systems as these simple units of each process is a pushdown system. But actually, when you take almost anything that has reachability decidable and it's close on the product with finite automata, you get the decidability of this complicated model when you put a parametric system and you have leader and contributors. Okay? So in this paper, we revisit the repeated reachability problem and give the exact complexity bind, which turns out to be the same as for reachability. And then we look at the safety and more general regular properties. And as you will see, we need to look at C-stuttering properties and not all regular properties. Why it's interesting to look at some other properties? Here's an example. So suppose you have this system here, and it works kind of like this. First, contributors propose some values by writing this to a register. Then the leader chooses one of those values, and then the rest of the protocol should work on this chosen value. So all the contributors should use also this chosen value in communication. Okay? And the properties you would like to see is leader eventually decides on some value. If a leader decides on some value, then contributors use only these values. And maybe some more complicated property on runs where only one value is used infinitely often, the protocol is correct. Okay? And now let us see what we can do with reachability, safety, etc. You see here is quantification for every n for every run. This is what probably you would like to know. But reachability problem that was studied is about there exists a run and there exists an n. So you need to negate all these properties. And for example, if you use reachability, you can actually solve the second problem, which is if the leader decides on the value, contributors use only this value, because negated, it would mean that I'm looking for a run, which is a counterexample, where there are some number of contributors, where the leader chooses one value and the contributor uses some other value. Okay, so this will be a counterexample. So safety can be used to decide that the leader eventually decides on one value, and then this property is more complicated. It's neither safety, neither reachability. Okay? So we address verification problems like this and like this. So first result that we have is that reachability, repeated reachability is p-space, and repeated reachability is to decide if this hash value should be written, can be written infinitely often. If there is a run that can read infinitely often this hash value, and this problem is p-space complete is the same as for reachability. And the reason I say this is also that we use word quasi-ordered in some, not exactly in the way to show decidability, but it's used for downward closure of a language, so we use downward closures of the language, and there is this very beautiful result that's saying that for every language, downward closure of the language is a regular language. So this way, it allows us to reduce a pushdown leader to a regular or finite automata leader, and this helps a lot in this setting. Then safety turns out more interesting because it's, well, as this bound here shows, there are different things that happen there. So what is the safety problem? We ask whether there exists a run, a maximal run, that does not write the hash value to a register. Okay, now we consider hash value as a bad value. And it's important to consider maximal run because otherwise an empty run just does nothing. It would not write hash value. So this is maximal run. And this problem is nx time complete. And actually for infinite runs, it's not that difficult. It's still p-space. But it's about finite maximal runs where the problems start or get interesting. And this is nx time complete. So to decide that the system kind of get to the stop and cannot do anything more, this is where the problem is. And I kind of can give you a glimpse of why. So for lower bound, we encode the tiling problem of 2 to the n grid. And then the idea would be that what will happen in a register would actually be just writing the values of the grid one by one, row by row. And checking horizontal coloring would be easy because it will just the leader that will check in local memory. This will just adjacent cells. And for checking vertical colorings, you kind of need to look to the n forward. And for this, you use a stack and the ability to count up to 2 to the n. And then there are delicate things happening anyway because you would like to ensure in this setting that you read all the symbols, that contributors do not skip through the symbols, do not read symbols twice, etc. And it happens that you can kind of manipulate it that way, and then that's why there are some duplicating things here, etc. That you can really force the system to work in sync and never skip any symbol or never write anything twice. So this also shows some power of the model, that you can force some synchronization between contributors and the leader once you have a pushdown system. And then the last result is about Stutter expanding properties, and it's still an exp time. So what are the Stutter expanding properties? It's in a sense the biggest class that makes sense here, the biggest class of regular properties. So a trace is a sequence of things that were written to a register, and the maximal trace, it comes things that were written with the maximal run. And stuttering expanding means that we do not distinguish situations when there was one activity of one contributor or activity of many contributors. So there is one value written of a contributor written once or twice, it doesn't matter. And it's kind of obvious that you want this because you do not control the number of contributors. You can always have the case that there are two contributors that behave exactly the same way. and just do the same writes or reads as a twins. So you need this property, because if you don't need this property, then if you don't have a C-stuttering property, then actually you would once again recover the situation what you can with a property force that there's only one contributor. And with this C-stuttering, you don't have this power, and it works, and then it's as difficult as safety. Okay? And in this result here, we use also another remark that's quite funny. I was writing one register there, but actually we can have several registers. And at first you can think that several registers and one register is exactly the same thing, because you can just have tuples of values. But when you think closer at this, you will see that having tuple of values and changing only one value in this tuple would require test and set. So actually simulating many registers with one register is actually quite involved and takes several pages, but it's still decidable and it still works. So this brings me to conclusions. So there are not so many models that are decidable of programs with recursion and concurrency, and this is because of this problem with two stacks communicating via register. And parametrization is one way of getting it. And we have studied this model, which is quite a bit more difficult, where you have one leader and parametric contributors. And then you have seen the results about safety and the C-stuttering properties. And it's quite surprising that this model is so robust. So almost whatever interesting thing you do with this thing, or reasonable thing you do, it turns out to be decidable. In other work, we have added spawn to this. So it's, you're allowed to spawn other processes. Instead of this one-level hierarchy, you have the hierarchy, which is also unbounded that way. And it turned out to be decidable once again. So there is something strange happening here that we do not understand still, even though the model is around for some time. But it's very robustly decidable. And as one open question is, we don't know whether we can do, for example, safety for this model with spawn, because technique is very different, and all these things I've talked here do not transfer immediately to the other case. Okay, thank you very much.
Questions? Any questions? Come to the mic. So do you have some implementation of your theory?
No, this is not implemented, so I don't have a table to show.
Okay, thank you. Okay, next speaker, you want to set up?